Today I'll tell everyone about Pebbles, our system that provides some brand new data management abstractions for modern operating systems. To motivate the need for these new abstractions, let me start with a few concrete examples. So here's a screenshot of my inbox from the default email application. I have an email here that's incredibly sensitive. It contains my social security number, and I delete it. Oh, thank you. Okay. Thank you. Okay. So here's a screenshot of my email application, of the default email application with a sensitive document. And I've deleted this document, and you can see that it's gone. But I ask myself, is it really gone? Are all pieces of it gone? And so what do you guys think? Is it deleted? Yeah. Well, as everyone said, no, operating systems don't delete data securely, and you might think that the parts of the email are still left in memory, or they're sitting around on flash, or somewhere in the cloud. And you're probably right about all that, but it's actually much worse than that. Due to a bug in this version of the email application, the attachment file is still left on the file system. And you have no way as a user to verify that the application did what you expected. So to add some visibility, we built a tool that can tell you when pieces of a high-level object, such as an email or document within an arbitrary and unmodified application, are left in persisted storage after deleting the object itself. And here I am showing a screenshot of this tool showing that the attachment file is left. And there are many more useful data management tools that can be built on the notion of objects. So have you ever looked at a file access log and wondered what is really being accessed here? And look at this log, for example. It consists of file-level accesses on an Android device. It's the kind of log you would get from many auditing tools. And you see a bunch of obscure-looking file names, and you have no idea what most of them correspond to. So for example, here's a file whose name is some hex number, and it must be a cache of something, but what? Wouldn't it be better if you had a document, or you had a log of the higher-level objects that were accessed, like the specific email or document? So I've given a few examples, but what is the general problem here? Today's operating systems lack appropriate abstractions for managing data. They see low-level opaque files and directories, while users think of high-level objects such as emails and documents. And therefore, the operating system has ceded all data management to the application sitting on top. And hence, the user is forced to rely on applications to correctly manage all of the data. And as we've seen time and time again, that applications do not manage data correctly. They'll often, they won't delete data, as I showed a moment ago, and they'll even use data for their own ends, such as advertising. So the research question we asked is there a way that we could teach operating systems about these higher-level higher-level object structures so that they can take over some of the data management functions, or at least provide the users with some visibility into how applications manage our data? Well, that's exactly what we've done. We've built Pebbles, which is an operating system level service that recognizes the structure of persistent objects and offers support for data management and transparency at a brand new level of abstraction, the level of the logical data object. So I've given you some examples of logical data objects and that Pebbles should be able to recognize in various applications, such as in email, and everything an email consists of, such as the sender, recipient, subject, and body, or objects in other applications like to-do lists or documents. And it exposes all of this structure to new data management tools built on top of it, which leverage the notion of a logical data object to provide users with increased visibility. In my example, such as in the tools I've hinted to, breadcrumbs and object log. So more formally, what we really want is to discover user-relevant data objects at a fine granularity and do so accurately with high precision and recall. And that is, we don't want leakage, which means that if an object should include a particular piece of data or a file, then we should include it in its LDO. This is high recall. And we do not want over-inclusion, which is, if an object should not include a particular piece of data or a file, we do not want to include it in its LDO. This is high precision. And most importantly, we do not want to add any new APIs that the application writer must implement that would to reveal the data structure to us. We want to have the operating system discover these structures in unmodified applications. So these goals seem impossible to achieve, don't they? And maybe they are in the most general sense. Each application might use an arbitrary file format. It can also map objects to files in many complex ways. One object may span many different files, or the same file may contain many of these high-level objects. So how can the operating system possibly distinguish between these individual objects? Well, it turns out that there's a huge amount of uniformity in how data is structured in modern operating systems, and that is in particular thanks to some high-level storage abstractions such as databases, object relational mappers, and XML key value stores that are popular and prevalent in modern operating systems like iOS and Android. So these files in these operating systems and the way applications store the data is not arbitrary at all. And that is our insight. We leverage this structural information that's already available, to recognize high-level, application-level objects, and we recognize them accurately, although a bit imperfectly. For example, we achieve a 97% precision and 91% recall across the 50 applications that we tested. But before I go off and tell you how to do this, I would like to show you a measurement study we did to show exactly how prevalent these new storage abstractions are. So the plan for the talk is I'm going to show you the results of this study. Then I'm going to go into the Pebbles architecture, which builds on those results. And then I'll show you some examples of data management tools that we've built on Pebbles. And finally, I'll evaluate our system. So let's talk about storage abstractions in Android and our measurement of them. So Android's persistent storage abstractions are not quite what we learn or teach in operating systems classes. In addition to the traditional file system abstraction, it provides an API for SQLite, which is an embedded relational database, and also an API for an XML-based key value store called shared preferences. A programmer can store all of his data in opaque files, but the framework is set up in such a way that structured storage is extremely prominent and easy to use. So the question we have now is, in reality, do applications actually use these high-level storage abstractions, or do they come up with their own? So to answer this question, we ran a measurement study. So we performed studies on two different data sets. The first is a static study of 470,000 free applications from the Google Play Store that we decompiled and analyzed. The second is a dynamic study where we execute the basic functionality in 98 applications. And we asked a bunch of questions in doing this study, such as what storage abstractions do the applications actually use? And do they use the default storage abstractions? And if not, what do they use? And also, how do applications organize their data? Is it all in SQLite, or do they tend to use multiple abstractions? So first we found that the storage abstractions included in Android are by far preferred. This table shows the number of applications that use SQLite versus various other storage libraries that we found for Android and Java. And their frequency in the top 100 apps, we don't see none of the applications use third-party libraries. But we did see all of them show up in the 470,000 application data set. Although the number of applications that use those pale in comparison to the number that use SQLite. So we performed a second study where we manually exercised 98 popular applications to find which storage abstractions they take advantage of in practice. And we found that the applications tend to use many of the abstractions, but do favor SQLite. 83 of the 98 applications use SQLite, 44 use the raw file system, and 23 use the XML key value store. And anecdotally, it looks like a lot of those that use the raw file system are using that to store large media files like images, ebooks, or video files. And they also use multiple storage abstractions for individual objects. For example, the email object, which you might think could be stored in a single database row, is actually stored across 3 SQLite tables, 2 database files, and then another file for each attachment. So the applications will use all of the storage abstractions and potentially in complex ways. So now I'm going to talk a little bit about the architecture of Pebbles and how that was influenced by this measurement study. So at the highest level, Pebbles plugs into these 3 popular storage abstractions to extract the inherent structure to reconstruct the logical data objects. Pebbles builds a device-wide object graph where each node is a database row, an XML key value pair, or a raw file. The object graph uses directed edges to record the relationships between objects. These directed edges encode a belongs to or a has a relationship, such as how an email attachment belongs to an email. And we define the logical data object to be the transitive closure of a node. Okay. The object graph is the key concept in Pebbles, so let me show you an example. Here is the email LDO. On the left side is the data layout on disk, where it is split between 3 tables and then attachment files. And the right side shows you the corresponding nodes in the email LDO. Each node is assigned a globally unique ID, or GUID, that Pebbles uses to address every object in the system. So now, how does Pebbles generate the relationships between these nodes? And I'll tell you in a minute, go in depth in a minute how. But just for an example, we can leverage structure inherent in databases like foreign keys to find some of these relationships. For instance, the body and attachment tables contain foreign keys to the email table. But things aren't really so simple. In the real world, developers don't always explicitly define these foreign keys. And as you can see in the graph, there's also a raw file that needs to be connected to the graph. So to construct this graph, we use a number of mechanisms and leverage taint tracking to very accurately discover these relationships. And we detect LDOs that are more complex than this one, which I'll show you in a moment. But before I go into that, I'll talk about the high-level architecture of Pebbles. So this is the basic architecture of the Android system. You have the base Linux OS at the bottom, the Dalvik interpreter, and then the Android framework, which provides the high-level data abstractions to the applications on top. So Pebbles modifies Android in 3 ways. First, we use TaintDroid, which is a mobile taint tracking system to track data flows and discover relationships. Second, we plug into the three storage APIs to obtain the persistent objects and track accesses to them to generate relations between them. And finally, we add a new system service to Android called the Pebbles Object Manager, which records all of the relationships and creates the device-wide object graph that I told you about. And the framework communicates with the object manager through the Pebbles registrar here. Then the Pebbles Object Manager also exposes these LDOs to data management tools sitting on top, like breadcrumbs or object log. So the key innovation in Pebbles is how we discover these relationships, which I'm going to go into next. So I'll walk through how the email LDO is created in detail. So we start out with one node per row or raw file, and which we added to the graph when those items were initially created. As I said before, the email is structured on disk with body and attachment tables that contain foreign keys to the corresponding emails that they're a part of. These foreign keys encode a belongs to relationship, telling us precisely how we should be linking the body and attachment nodes to the email in our LDO graph. Except that the application doesn't explicitly declare these foreign keys in the schema, but copies the email's key into the body and attachment table as the orange boxes show. So next I'll show you how we use taint tracking to detect, very reliably I might add, that to detect these foreign key relationships, and I'll focus on the email body relationship as the email attachment relationship works in the same way. When data is read from some row, we taint that data with the row's GUID, and when the data tainted with some GUID is written into either a row or a file, a new relationship is added to the object graph. Okay, so how does this help detect foreign keys? Well, when the application took the email's key from the email row in order to place it into the body row, the key itself was tainted with the email node's GUID. And when the application wrote the key into the body table, the new relationship was created pointing from the email node to the body node, and in this case, the attachment as well. This approach works very well, and while it may seem like a heuristic, I'll remark that it's rooted in the fundamental way that databases work. Okay, so now we have the relationship between the rows, but there's still an attachment file that is not corrected. Here we use a very similar principle because the attachment file is also indexed from the database. Its file name contains a reference to the email to the key in the attachment table, similar to a foreign key, and which is shown here, which is the last link in our LDO graph. So Pebbles embeds a number of mechanisms for object relationship detection, and all of them are rooted in common programming practices that we observed in our experiments. And you can see our paper for more details. So Pebbles uses the relationship discovery mechanisms to discover LDOs in many applications. And I've shown you the email structure, but I've shown you the email structure here. But an email application will contain multiple emails, such as the second email that doesn't contain an attachment. So an email will be part of the mailbox LDO, which represents email folders like inbox or spam. And then both emails and mailboxes will be part of an account LDO. Some other examples of LDOs that Pebbles discovers are the to-do list and to-do list items in Wunderlist on the top right,
And then on the bottom right is the CW Money application, which allows a user to associate an expense with an account and file that and associate those expenses with categories. And this graph is unique in that the expense object is part of two LDOs, the category and the account. So to track the relationships, we use a modified version of TaintDroid. Using TaintDroid out of the box led to taint explosion due to its coarse-grained tainting, where each array gets a single taint. We changed it to implement a fine-grained array tainting, where each element in the array maintains its own taint. In our experience, this modification made a huge difference and abated our taint explosion problem. We made several other pretty useful modifications to TaintDroid, all of which are available on GitHub now. So now I'm going to talk a little bit about the deletion auditing application Breadcrumbs that I mentioned earlier in the presentation. So using Breadcrumbs, a user can select an item that should be tracked for deletion, such as in the screenshot where the user selected email message to be deleted. So after deleting the email, the user will navigate to the Breadcrumbs Explorer tool on the right and to see if the data was deleted as requested, as in this case it was not. So how does Breadcrumbs find the file left behind? Well, it obtained the object structure, the LDO, from the Pebbles Object Manager, and then after the user deletes the object, Breadcrumbs traverses the LDO to test if the data has been removed from the disk. And in this case, the attachment file is still left behind. So in addition to Breadcrumbs, we've built three other applications. The first one is Object Log, which provides auditing at a high-level auditing at the level of an object, and can provide other information such as like an image in this case, or the object shown earlier, or Pebbles diffc, which provides cross-application object-level access control to do things like lock an object to a single application. And we've also built the last application, which is called Hide It, which allows a user to mark individual objects to provide fine-grained encryption and protection. So now I'll talk about evaluating Pebbles. So when evaluating Pebbles, we pose these 4 questions. We don't have time to go into all of them here, so I will focus on the first 2. So our principal evaluation is whether Pebbles correctly identifies objects. So we selected 50 applications that store data on the device and manually identified 68 unique object types by examining each of the applications and looking for user-recognizable objects. So Pebbles identifies most of these objects correctly, many of which are not included on this slide. So in the default email application, Pebbles correctly identifies emails, folders, and accounts. In browser, Pebbles identifies bookmarks and history items. In Wunderlist, lists and items. And in the CW Money application, it correctly identifies accounts, expenses, and categories. Overall, Pebbles identifies 60 out of the 68 unique objects correctly, which is pretty accurate for a completely unassisted mechanism. We saw 6 of the 8 objects that Pebbles did not recognize correctly. We saw 6 of them that showed leakage and 2 of them that showed over-inclusion. One that showed leakage was the Bloomberg Finance application, which allows a user to select stocks and track the prices of them. And in this case, the stock object was not correctly related to the price. And this was because that all of the relationship is actually done on the server side and then written directly to the device. So there is no data flow in between the rows for Pebbles to see and relate. And an application that showed over-inclusion was the popular Life Church Bible application, which uses non-primary key data to relate objects. In this case, Pebbles cannot refine the relationship into a directional relationship. Then we also evaluated the Pebbles performance on a suite of macro benchmarks, performing tasks, common tasks in email, OI Note, and the browser. And we saw overheads up to 360 milliseconds with an average overhead of about 131. So last, I'll talk to you about some findings that we found when evaluating those same 50 applications with Breadcrumbs. So of the 50 applications we evaluated, 18 of them showed some kind of improper deletion, which seems like a lot. And some of these applications include popular ones like Twitter, the email application, and Evernote. Some of the applications would partially delete data, leaving behind bits of the object graph, while others just hid the data from the UI and did not delete anything. So the next time you try to delete some kind of data from your application, it's a good chance that it's still there. And now we'll go into conclusion. So some some of the conclusions that we have is that we can use the inherent structure in these high-level data abstractions to generate objects, which we can use to provide users with transparency and protection. So, thank you.
Hi, Ashwin Gail, University of Toronto. Nice work. I was actually just curious about whether, other than the foreign key relationships and the name of the file relationships, whether you have other relationships that you look for, and whether you find those other kinds of relationships.
Okay, so all of the relationships that we find are basically refinements of data flow relationships. So, Pebbles can use this TaintDroid to track data through the system, and then once data is written into an object, written into another file or database row, this generates a bidirectional relationship because there's some kind of shared data. And from there, we refine that down to be a unidirectional relation using the foreign key, or refine it using like an access based on access, whether it's a foreign key or if it's used to access a file path, or in the case of the key value shared preferences, if it's used to access the key. So.
Okay, thanks.
Okay.
Hi, I'm Jonas Wagner from EPFL. I think this is really cool, and I just wondered if you had faced issues with applications that try to encrypt their storage.
In this case, no, we didn't come across any applications that tried to encrypt their storage, but we found in the 470,000 application study we did, several hundred that used a library called, I think it was SQLite Crypt, that encrypts the SQLite storage. So we didn't come across any in our evaluation. It wasn't one of the popular applications, but it does happen.
All right, let's take your speaker.
Thank you.